In all the situations we've studied so far, the order in which objects or items or people took or were placed in, that mattered, and each different arrangement with a different order was distinguishable or different. Well, there are situations in which that's not true. And in those situations, we count, instead of counting permutations, we count what's called combinations. So that's an important difference to remember. Does order matter? If it does, then count permutations. If it doesn't, count combinations. Let me show you what I mean. Suppose I have 8 different shirts and I'm going on a vacation and I'm going to just pack 3 of them. Well, how many different combinations are possible? If I label my shirts A, B, C, D, E, F, G, H, and let's say I take shirts A, B, and C. Well, wouldn't that be the same as taking shirts A, C, and B? Or B, A, and C? Or B, C, and A? C, A, and B? Or C, B, and A? Aren't those all the same? I mean, I don't really care in which order I pack them. As long as I have them, I have them. If I don't have them, I don't have them. Okay, and so this is a situation in which order doesn't matter. The combination of having those 3 shirts is the only thing that matters. So all of those 6 permutations of those 3 items are one single combination. Alright, do you see the difference? So if I want to count the number of combinations of 3 shirts from a group of 8, if I do it using NPR, that is 8p3, or 8 factorial over 5 factorial, that's counting all the permutations. And as I said, for the unique combination A, B, and C, there were 6 different ways to make permutations of those items. So I'm overcounting by a factor of 6. And 6 happens to be 3 factorial. So the way to calculate combinations in this situation isn't just 8 factorial over 5 factorial, it's 8 factorial over 5 factorial and then over 3 factorial. Okay, and that comes out to be 56 different ways. So the number of combinations is less than the number of permutations. It's 6 times less, because for each combination, say E, F, and G, there's going to be 6 permutations that really don't matter to us if all we care about is do we have shirts E, F, and G. So when you find yourself counting combinations, here's the formula that you can use. The number of combinations of n items taken r at a time, NCR, is n factorial over n minus r factorial over r factorial. So it's the same exact thing as NPR except for that extra r factorial in the denominator. But it makes a big difference. It's also sometimes written like this, a bracket with n on top of r. That means NCR. Okay, and it's sometimes also written C of n comma r. Sorry about all that, but different people use different notation. To find this, just like to find NPR, you use the math menu, PRB for probability, and then find NCR. So for example, try making 8 NCR3 and see if you don't get 56 like I did for the example we just went through. Okay, let's look at some more examples. This time we'll use the examples in section 10.2 of your book. Example 1. On page 644, there's 10 different kinds of juice, and we're going to pick 3. Doesn't matter in which order we choose them, we're going to get 3, and we're going to get the same 3 no matter which order they're given to us. So that would be 10C3. And to see how this works out, that's 10 factorial over 10 minus 3 factorial, which is 7 factorial, and then also over 3 factorial. So 10 factorial is 10 times 9 times 8 times 7, blah, 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 all the way down to 1, and 7 is 7 all the way down to 1. And so most of that's going to cancel out, leaving me with 10, 9, 8. And then there's also this 3 factorial on the bottom. And if you work it out, it turns out to be 120. Okay, so 120 different ways to choose 3 of 10 juices. Examples 2 is kind of interesting because it really highlights the difference between permutations and combinations. Right, if we have 5 people and we're going to choose 3 of them to be on a committee or a group. Right? On some committees, there's no president or vice president or anything, and everyone on the committee is equal. So in part A, that's the idea. 3 equal committee members from a group of 5. Well, if they're equal, then the order doesn't matter, and we use combinations, 5C3 or 10. Now, if we choose a president, a vice president, and a secretary or something like that is what they're doing in part B, then the order matters. Who gets which spot on the committee is important. And when order is important, we count permutations, not combinations. So 5p3, which is 60. Right? The number of permutations is 6 times bigger than the number of combinations because each combination of 3 people, you can find 6 different ways to order those 3 people. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1, right? So they're always slightly different combinations and permutations. Example 3 is a bit more complex. We have 7 CDs, 5 cassette tapes, and 3 videotapes. Do you guys even know what cassette tapes and videotapes are? I guess it doesn't really matter. They're just some other things, right? And we're going to choose 2 CDs, 3 out of the 5 cassettes, and 1 out of the 3 videotapes. So what we can do in this complex situation is break it down into 3 simple situations. How many ways can I get a combination of 2 CDs from a total of 7? Well, 7C2. I don't care what order they're in. And 5C3 for the cassettes, and 3C1 for the videotapes. And those are all right, 21, 10, and 3. And the fundamental counting principle says that if we want to find out the total number of ways in which this compound event can happen, we just multiply those 3 together, and we get 630. There's a funny thing about combinations. Check it out. 7C2 is 21, but 7C5, that's also 21. In fact, here's the sequence of 7 choose everything, right? 7 choose 0, well there's one way to choose nothing. There's 7 ways to choose 1, 21, 35, 35, 20. You can see that it's symmetric. And it makes sense at the other end too. There's only one way to choose all 7. So why is this? And there's a weird explanation for it. If you choose 2 things out of 7, then you have to also be choosing to leave 5 out. You have no choice, right? And so if you choose 5, you're choosing to leave 2 out. And the number of ways that you can choose to keep 2 or choose to leave out 2 has to be the same. And so it's a general fact that NCR is equal to NC n minus R. Think about that for a while. Finally, getting back to the idea of probability, example 4 shows us how we can use combinations to measure the probability of an event. Suppose there's a survey done and 25 people were asked if they approve of or disapprove of particular policy. 17 of the 25 were in favor and 8 were opposed. Now, if we choose 6 of the people that were interviewed randomly, what's the chances that 2 of them will be in favor and 4 of them will be opposed? Well, we can break that down into 2 simpler events. The chances of getting 2 in favor, well, there's 17 that were in favor out of the total of 25, and only 2 of them and we need to choose 2 of them, right? So 17 choose 2 for that part. And then of the 8 people that were opposed, we're going to try to choose 4. And so there are this many ways to do that. Making a compound event by multiplying them together gives us the total number of outcomes in the compound event. So we're almost done. But that's the number of ways that we can get our result. That's the number of outcomes in the event we're after. 2 in favor and 4 opposed. Okay, but how many ways are there to choose 6 people out of the 25? Right? That's the number of outcomes in the sample space, and it's 25C16. This is really complicated. Go back and look at it again. But what we're doing is in the numerator, we're trying to count up the number of ways we can get 2 people in favor and 4 opposed. And that in itself was a compound event. And then in the denominator, we're counting up the total number of ways to choose 6 people out of 25. This turns out to be about 5%, 0.05 or 5%. This looks a lot like when we calculate probabilities for cards in poker and other games. So that'll show up again later. All right, well, get to work. Page 647, 9 to 43 odd. Good luck, guys. Ask me questions.